Okay, let's go over the number one in the practice quiz, curve sketching quiz. Pretty much the idea is here's this function, and we want to be able to graph it completely without plotting points. Like, how can we use calculus to figure out exactly what that graph looks like, where all the major parts are, so we can graph it really well without doing the whole plotting points thing, or using Desmos or something. So let's go. So first it says find the critical points and determine if they're local max or min. Okay, critical points are where the slope is 0 or where the slope is infinite. So the first thing we do is take the derivative. So the derivative, let's call it y prime or f prime of x or whatever. So let's just say y prime is easier to write. The derivative is easy. 3 times 3 is 9, so 9x squared. Minus 2 is 4x minus 4x minus 2. That's the slope, the derivative. And then we want to know where that's infinite or where it's 0. Now there's no dividing by 0 here, so there's no infinities. So that's easy. There's none of those. So we just basically we need to figure out where it's equal to 0. There's also no sharp points, no weird stuff going on like that. So basically we can figure out where it's 0, and where something like this, a quadratic is 0, is going to be either a max or a min, and that's the second part. Okay, so we set it equal to 0 and now solve it. It looks like this is purely a quadratic formula, right? And then you always hope that you can factor it. I don't think there's any way we can factor this. It looks kind of tricky. So we just use the quadratic formula. So x is equal to negative b. So the negative b is 4 plus or minus square root of b squared, which is 4 squared. Negative 4 squared is 16. Minus 4 times a, which is 9, times c, which is negative 2. All divided by 2a. A is 9, so 18. Okay, so that's 4/18, which is 2/9. So 2/9 plus or minus the square root of 16 plus, right? Because minus and that's negative, so 16 plus. 2 times 4 is 8 times 9 is 72. Or 18 times 4, yep, 72. So 16 plus 72, which is 88. I'm doing too much in my head. 4 times 18 plus 16. Yep, I got that right. Square root of 88 divided by, why did I write square root inside the square root? Square root of 88 divided by 18. Okay, this is going to be, sometimes if it's going to be a pretty number, we can try to figure out the pretty number here, but this is not going to be a pretty number. So let's just decimalize this thing. So that's 2/9 is 0.2222 forever. So that's 0.2222 forever, plus or minus square root of 88 divided by 18, plus or minus 0.521. 0.521. So that's, I get equal to 0.743, close enough, 3 decimal places, or the minus 1, 0.22222 minus 0.521 is 0.2987, 0.299, or negative 0.299. Okay, so those are the two places. There's only 2 of them. The 2 places where the slope is 0, at 0.743 and at 0.299. Now, are they maximum or minimum? And the way you figure that out is we can look at this, we can plug that in to our derivative and figure out if, like, at slightly before 0.743 is the derivative positive or negative, right? Because if it's a maximum, it's going up like this. So the slope goes from positive slope, positive derivative, negative derivative. So like at 0.7, we could plug 0.7 in here, see if it's positive or negative, and then plug something bigger than 0.743 is, we could plug a 0.8 in, and if it's negative and this one's positive, we know it's a max. And if it's the other way around, we know it's a minimum. If it goes from negative to positive, we know it's a minimum. That's kind of a lot of work. I mean, it's not too bad. The other way to do it is the second derivative. If the second derivative is positive, that means that, let's see, second derivative being positive means that it's a minimum, because the slope goes, the second derivative positive means it's changing positively. The slope is changing positively, so it's going from negative to positive. So here the second derivative is greater than 0, because the slope is changing in a positive way. It's going from negative to positive. And here the slope is going from positive to negative, so the second derivative is less than 0. So there's two ways to figure out if it's a max or min. The second derivative test, or the plugging in values in either side and figuring out the slope. Let's do second derivative test, because in this case the second derivative is really easy to take. So the second derivative, y double prime, 2 times that is just 18x minus 4. Right? I mean, that's real easy, so you might as well just do it this way. If it's a really hard second derivative, then it's probably easier to plug in numbers on either side of the peak. And you want to be pretty close, right? You don't want to interfere with the other point. But this is easier. Okay, so the second derivative at 0.743, that looks like it's going to be positive. 18 times 0.743 is 13.374 minus 4. I get 9.374. So therefore 0.743 must be, second derivative is greater than 0. It's a minimum. So 0.743 is a minimum. Now it says you want both x and y values. So we know this is a minimum, which means that the other one pretty much has to be a maximum. There's no way you can have two minimums next to each other without a peak in between, if it's a nice well-behaving function. But let's figure it out anyway. Let's just check and make sure we did the math right. So we plug in negative 0.299, plug that in here, so 18 times negative 0.299 is negative 5.382 plus 4. I get negative 1.382, so sure enough it is a maximum. So it's just a really good check to do it anyway, just to make sure that it all makes sense, we didn't do some math wrong. If we get both positive, we did something wrong. If one's a max, one's got to be a min. Okay, now we got to figure out the actual points. So if x is 0.743, so if x is 0.743, then y, we just have to use the original equation. Okay, we got to go all the way back up to here, use the original equation. It's kind of a pain. Y is 3 times 0.743 cubed minus 2 times 0.743 squared, minus 2 times 0.743. And this is some calculator work, unfortunately. And the reason why we want the points is because we're going to graph them. So we want to get the major points, the max min, so we can actually graph them. So we know the x, we want to know the y too. So that's why we're doing this. So 0.743 y dx 3 times 3. I guess 1.23 minus 743 squared times 2 minus 1.1 minus 2 times 0.743 times 2 minus 1.486. Let me check that. 0.743 x squared times 2 equals. Yep, I think that's right. Okay, so that negative minus 1.486 plus 1.23. I get negative 1.36. So negative 1.36. So that's our first point. And then the second one, so I'll write it over here. So 0.743 and then negative 1.36. That's 1 point. And then the other point, we plug in x is negative 0.299. So y then, and I'm just going to plug that in, same as this, by plugging 0.299 here and cube it and all that kind of stuff. 0.299 times 3. Oh, did I multiply by? Yeah, I had to. Let me do that again. 0.299 times Okay, it's a lot of calculator work. Y the x3 times 3 equals, so that's negative 0.08 plus, because, no, it's minus again, sorry, minus 2 times minus 2 times 0.299 squared times 2, 1.179 minus 2 times negative, so that's plus, so 0.299 times 2 minus plus 0.598, which is 0.598 minus 0.179 minus 0.08. I get 0.339. So our other point is 0.299, negative 0.299, and then 0.339, excuse me, 0.339. So those are 2 points. This one is a max, this is the max, and this is the min. So here I'll circle those so we can remember them for later. Those are the 2 points, and this is a minimum, and this is a maximum. Okay. Okay, that is the first part. These things take a long time. It's just a lot of work to go through all this, but that's okay. Okay, find the other extrema, which means the endpoints of the interval, both the x and y values. Okay, so we said we only care about this function between negative 1 and 1. So we know that in between here, and these are between negative 1 and 1, right? So 0.743 is smaller than 1, and negative 0.299 is smaller than negative 1. So, okay, so both these points are within our interval between negative 1 and 1. But what about the interval points themselves? What's happening there? And those are the x values. So when x equals negative 1, y is equal to, so you plug in negative 1 here. So 3 times negative 1 cubed minus 2 times negative 1 squared minus 2 times negative 1. We've got to be super careful with the negatives. Negative 1 cubed is negative 1, so that's negative 3. Negative 1 squared is 1, so, but there's still minus 2, and then that's minus 2 times negative 1, which is plus 2, so it's just negative 3. So 1 point is negative 1, negative 3. The other one, when x is equal to 1, it's the same thing here. Y is equal to, but here it's 1, so it's 3, minus 2 still, 1 squared is 1, plus 2, right? So minus 2 times 1, wait, no, that's minus 2. Minus 2, because it's minus 2 times 1, yep. So it's minus 2 times minus 2, so that would be 3 minus 4, negative 1. So the other point is 1 comma negative 1. Okay, so we know all the interesting points. We know there's a maximum and a minimum in the interval between negative 1 and 1 that we're going to graph, and at the interval itself we know their values. At negative 1, y is negative 3, at 1, y is negative 1. Okay, then it says what are the coordinates of the global maximum in the given interval? What's the biggest y value and what's the smallest y value? So we have 4 points. The biggest y value, this is the second one. Here we have negative 1.36, 0.339, negative 3, negative 1. So the 0.339 is the biggest, right? So the biggest is this point here, negative 0.299 and 0.339. It's the only positive y, so it's obviously the biggest. So that's the max, the global max, because it's the overall max. There's other maxes, but it's the biggest point on the interval. And then the global minimum, what's the most negative? Here we have a negative 1.36, negative 1, negative 3. This is the most negative. So it's one of the endpoints, but that's okay. So the smallest, most negative or the smallest point is this one. That's the global minimum, because it's the overall minimum on our graph. And we want to know those because when we graph it, we got to make sure that our we only need to go as high as y of about 0.339 and as low as y from -3. So we want to make sure we go all the way down to -3 in our graph and as big as 0.339. So this really helps us graph it too, knowing how big to make the graph. Okay, then part D, find the x-coordinates of all the inflection points and justify their inflection points. Okay, if we have a graph like this, nothing weird happens, and we know we have a maximum and a minimum. So we know that our graph has to look like we have a maximum. Let's see, which one comes first? The minimum is a 0.743, maximum 0.299. Okay, so it looks something like this. We have a maximum, minimum, and then it's going to go to infinity on either side, except we're chopping it off at -1 and 1. Okay, so it's going to look something like that. We know there's got to be one inflection point. In between every max and a min, there's a point where the slope switches over from getting more and more steep to less and less steep. Otherwise, there are no more, because this goes off to infinity, that goes off to infinity. And we want the inflection point because on this side it's going to be concave down, and on this side it's going to be concave up over here. So that switches over right there. And in this case, the inflection point, here the second derivative, y double prime, is, let's see, less than 0. Here the second derivative is greater than 0, and right there at the inflection point the second derivative is equal to 0. So we want to know when our second derivative is equal to 0. That's the inflection point. There should only be one right here, right, because of the nature of this graph. Okay, second derivative we already figured out was 18x minus 4. So this is pretty easy math. Put the 4 over there. So 18x is equal to 4, or x is equal to 4/18, which is 2/9, which we know is 0.222222. So that is the inflection point. It happens at x equals 0.222. So when we graph it, we know that we go to x about 0.222 something, 2/9, and we put a dot there, and that should look like, you know, somewhere right in between. It's not always halfway in between. It's not always, these curves aren't symmetrical, but usually around halfway in between the peak and the valley. Okay, that's our inflection point. So x is equal to 0.222. And we don't need to figure out the y value, we just need to find the x value, put a dot in our curve, we know it's there. Okay, over what interval is the graph concave down? Well, like we just said, it's going to look something like this. So we know from -1 to the inflection point, it's concave down. The inflection point is 0.222. So from -1 to there, and we can write it like this because those are the x values from x equals -1. Because remember, we only care about from -1 to 1. So if I had asked for concave up, which I should have, I should have said both, then it's 0.222, put 3 in there just for the heck of it, 0.222 all the way to 1. That would be concave up, because from the inflection point all the way over to 1, really to infinity, but we only care about to 1. So this would be down. Didn't ask for it, but whatever. So that'd be up. Okay, over what interval is the graph increasing? Where is the slope positive? Again, from a quick little sketch that I did, it's going to be positive in two places. From -1 to the max. So from -1 to increasing to right to this peak right here, which we know happens at -0.299. And we could put regular parentheses, so it is including, I think we're including the interval, so it's good to put the bracket ones. And also it's increasing from the minimum value to 1, right? This minimum value to 1. The minimum value was 0.743. That was our minimum. So also from 0.743 to 1. Okay, from the minimum value here, which is 0.743, this was at 0.222, sorry, at -0.299, and then this one's at 0.2. Now, okay, so that's where it's increasing. Now, if I said decreasing, which would be a good question, then it's from here to here, and that's it, right? That's the only place, there's only one of them. Because the slope is negative going downhill. So you would have said if I had asked for decreasing, we would have gone from this point, which is -0.299, to the minimum, which is at 0.743. So I'll just write that down. So decreasing would have been from the peak here, negative 0.299 all the way to 0.743. Basically whatever's missing from here, right? The middle, right? The middle right here is where it's decreasing, which is this part. Okay, now we can draw our graph. Let's see, I gave you lots of room here. We know negative, we got to go down to at least -3. So let me put a -3 here. So that would break this up into thirds. And then we go up here, and we only need to go to 0.5 positive, so we're wasting all this space, but whatever. We have plenty of room down here. If that's, let's see. So we could make, if we want to make the x-axis the same scale, if we go all the way to -3 down here, then this is only -1, and this is 1, so that's the interval we're worried about. So that's a pretty narrow range here, right? Which, oh well, that's just the way it's going to have to be. We're going to not have to use a lot of this paper. Okay, so let's see. Let's put our numbers in at -1. We know that it's -3, so that's the point where it's -3. Because I'm looking over here, right? The endpoints, -1 is -3, and 1 is -1. So -1 is -3, and a 1, it's -1. So here's another point. Those are the endpoints. And then in the middle, our max and mins are 0.743, -1.36. 0.743 is about 3/4 here, and it's -1.36. So here's -1, so maybe around right here. And then the maximum was -0.299, so negative about 0.3, somewhere right here, and 0.339. This is 1, so I'm not doing very like about a third of the way up there, right? That is the maximum. Now we connect the dots, and this is the max. It's going to be a curve, so we want to peak it out there. That's the tricky part. So you draw a graph like this, and it peaks right there, and then it comes down, and we want the trough to be right there, and then it goes back up. And the last thing is at 0.222, we know there's inflection points. So here's 1, so here's a half, so 0.22 right about there, which makes sense, right? It's getting steeper, 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 and then less and less steep. So from -1 to 1, this is what our graph looks like. If we put this on Desmos, you'll find it looks really similar to that if we did everything right. And so, I mean, so this is again a very accurate picture of the graph, just from using calculus and knowing where the peaks are and the inflection points and everything. And of course I could have done a little bit better. This looks kind of rough here. It's probably a nice smooth curve, but yeah, good enough. Okay, I'll do a second video because this one's getting pretty long on the next part, on part B, on number 2. So, okay, we'll see you then.